Yeah, good evening, everyone. I'm Akash Jyoti Pathak, and I welcome you all to the week 3 problem solving session of the NPTEL course NMR Spectroscopy for Chemists and Biologists. So I will wait for 5 minutes and then I will start today's session. I hope all of you have gone through the week 3 lectures. So I will share today's slides. I hope the slides are visible. Yeah, so I'll start the session now. Today we will start discussing about a few sample questions related to the week 3 lectures that will help you solve the assignment. And also, if you have any doubts, I can take up the doubts and we can also solve such questions. So yeah, hello everyone. I'm Akash Jyoti Pathak. I am a PhD scholar in the Department of Biosciences and Bioengineering at IIT Bombay. I am currently in the second year of my PhD, and I'm working in NMR spectroscopy lab. So let's start. Uh, so the first question is, which of the statements are correct regarding the proton spectra of ethanol? In the last session, we discussed about several concepts like chemical shift, and then after that we had moved into what the various spin-spin coupling, J coupling, all those concepts we had seen in the last week. Now in this week, we will discuss few concepts related to week 2, and we will also discuss in the later half of this session, we will also discuss questions that will help you in solving the week 3 assignment. This ethanol, I had already discussed this concept in week 2, but just for a quick recap, I have added this question so that we can so that I can so that you can you can try this question, and then we can move on to the further questions. So the options over here are first option is a peak at 4 to 5 ppm, a peak at 1.5 to 3.5 ppm, a peak at 0.5 to 1.5 ppm, and the fourth option is all of the above. So ethanol, this proton spectra of ethanol has been discussed several times in the lecture also, and it is the one of the most simple spectra for and if you want if someone has to understand about the chemical shift and stuff, then the best way to start understanding is to first understand the spectra of ethanol. As you all know, the chemical formula of ethanol is CH3, CH2OH, right? CH3CH2OH, and the proton spectra of ethanol was first recorded in TIFR by Professor Bharmati. And what he observed that when the spectra of ethanol was recorded, he observed three peaks. He observed three peaks. So if we record the proton spectra of ethanol, so here on the x-axis we have the chemical shift delta, which is in ppm, and on the y-axis we have absorption of the absorption of frequencies depending on what on the nuclei we see. We record the so here what we see in ethanol. In ethanol we have three proton. We have three different protons. One is this methyl proton, one is this methylene proton, and another is the hydroxyl proton. Okay. Now depending on the, as we had discussed in the in week 2, that depending on the chemical environment of the nuclei, the nuclei will absorb a particular frequency, which will be the resonance frequency of that nuclei. So here in ethanol we see there are three protons. So let us label these three protons. So this is A, this is B, and this is C. Okay. Now, if we see the methyl proton, then what we can see is that the methyl proton will have a will absorb at a particular frequency, right? Will absorb at a particular frequencies, and all these frequencies are recorded with respect to a reference frequency. That reference frequency is that of TMS. Is that of TMS. Now, the methyl proton is most shielded. is more shielded. Therefore, it absorbs. It has a peak at a up. It has an upfield shift. It is present near the 0 ppm, right? Because it is highly heavily shielded, and therefore the peak of methyl proton is observed in the upfield means which is near to the 0 ppm, which is near to the peak of TMS. Then if we see, then moving to the methylene proton. So the methylene proton will at a have a peak somewhere about here, right? We'll have a peak somewhere about here, and the ethanol proton, because this proton is attached to the is attached to the electronegative oxygen atom. This will move downfield. This will move downfield, and its spectra we will observe the peak of this of the ethanol proton at a much larger at a much larger delta value, at a much larger ppm value. So we will observe three peaks. One is for the methyl proton, one is for the methylene proton, and another is for the proton which is attached to the electronegative oxygen. Now the intensity of the peak. So this is just a representation. So this is A, this is B, and this is C. So this is just a rough representation of how many peaks we will observe. Now, what will be the intensities of these peaks? The intensity of the peak will depend on the number of protons, number of protons that are attached to the carbon group. So here we see there are 3 protons. So since there are 3 protons, the intensity of the peak will be higher. Intensity of the peak will be higher. So the integral of the peak, if we if we integrate the area under this peak, then that will correspond to 3 protons. That will correspond to intensities of 3 protons. Now, here there are now the methylene group has 2 protons. So the integral of this peak will correspond to 2 protons. Okay, and the intensity will be slightly. It will have a slightly shorter intensity than the methyl group, and then we move to the hydroxyl proton. The hydroxyl proton, there is only one. Hydrogen group. So the intensity will be further lower than that of the methyl and the methylene groups. Okay. So the intensity will roughly be in the ratio of 1:2:3. So this will be 3. If we calculate the integral, this will be 3. This will be 2, and this will be 1. Okay. So now in the last lecture also I had shown a figure where the ppm values of different groups had been were shown. So you need to have a rough understanding of where we get the methyl shift, where we get the chemical shift of methyl group, where is the chemical shift of methylene groups, where is the chemical shift of OH group. So you need to have a rough understanding of, you do not need to memorize the values, but a rough understanding will help you in solving such type of questions. So yeah, so here you can see in this figure, as you can see that the methyl group has a absorbs at a frequency at a ppm value of near about 1 ppm. Then the methylene group has absorbs at around 3.8 ppm, and then the hydroxyl protons absorb at a frequency of around 4 to 5 ppm. Okay, so as you can see in this figure that there are 3 we obtain in 3 peaks, and I'll just rub this figure so that you can read what is written here. So yeah, the spectrum shows 3 lines belonging to the methyl, methylene, and the hydroxyl protons in the molecule. These 3 groups of protons have different electronic environments, and consequently they resonate at different frequencies. The intensities of the individual lines are in the same proportion as the number of protons of each type, namely 3:2:1. Okay, so 3 for methyl proton, 2 is for the methylene proton, and 1 is for the hydroxyl proton. Okay, and So the reason why they are showing different chemical shifts, I had explained in the last lecture that it depends on the chemical environment. So this proton is, if we see the HB proton, this proton is bonded to the carbon group, and this carbon is surrounded by the methyl group and the hydroxyl group. And depending on its environment, whether it is it that will decide whether it is shielded or whether it is deshielded, and depending on that factor, depending on these factors, it will control. Depend on these factors will control where we will obtain the chemical shift. Okay. Yeah, so last in the last lecture also we had discussed about spin-spin coupling, but let's discuss this concept in more detail, because today I will discuss few questions that were in the in assignment 2, so that if you have any doubt in week 2 assignments, then you can go through this lecture and you can understand the concepts. So what is spin-spin coupling? So let us understand this with the help of an example. So we are taking the same example of ethanol. So if we see the ethanol molecule, and if we record the proton spectra of ethanol molecule, we see that the what we see, we primarily we see three different peaks. One is for the methyl proton, one is for the methylene proton, and another is for the hydroxy proton. Now, if we look at these peaks in more detail, what we see that this methyl proton is further split into how many peaks? It is further split into three peaks. If we magnify the spectra, and if we look at this section in more detail, what we find is that this this is actually composed of three different peaks. The single peak has is act is it is not it is not a single peak, but it has three peaks, and these three peaks are in the ratio of the intensity of these three peaks are in the ratio of 1:2:1. So this is 1, this is 2, this is 3, and this is called a triplet. This is called a triplet. Okay. Similarly, if we magnify this, the peak that we have obtained for methylene proton, we what we find is that this methylene proton this is not a single peak, but there are actually four peaks. There are how many peaks? There are four peaks. If we magnify this,
Hello, hello, hello.
hello, am I audible?
Now you are audible, but before time you are not audible to me.
Okay.
But your video is paused.
Yeah, I'll start the recording. Right.
Okay. Thank you.
So is the screen visible? Would do.
A screen is visible, but your video is paused.
My video, I'm not visible.
You are visible, but not moving.
Okay. Okay. So what is being displayed in the screen? What can you see on the screen?
A spin coupling concept.
Okay. 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 Yeah. Yeah. So till which part were you able to hear? This one,
Mm, 4 peaks.
yeah, 4 peaks, right? Yeah. So I
Yeah.
was discussing about spin coupling. So if we look at the methylene peaks, methylene peak, and if we magnify it, we can see that this methylene peak has actually there are actually 4 peaks that make up this that are in this peak. And how does these 4 peaks have an intensity in the ratio? Have an intensity in the ratio 1:3:3:1. 1:3:3:1. And so this type of spectra, the type of splitting of this single peak into 4 peaks is called a quartet. It is called a quartet. And and in the case of methyl group, we see that the this peak is split as actually it is split into three finer peaks, and these three fine peaks are called triplet. So why is this happening? So this is happening because of the spin coupling. And what is spin coupling? We will understand it in the next slide. So what does this slide say? That both these fine structures are a consequence of spin coupling between the methyl and the methylene proton. So coupling, what does coupling mean? Coupling means that this methyl group is coupled to the methylene group. Methyl group is coupled to the methylene group, or it is joined, or it is connected with the methylene group, and because of this, there is this the spin the nuclear spin of this proton is coupled to the nuclear spin of the proton in the methylene group through the bond, or through the electron through the electron bond that is connecting these two groups. Okay. So what is spin coupling? The spin coupling refers to the interaction between spins that leads to the splitting of resonance lines in the NMR spectra. So what did we see in the proton spectra of ethanol? We saw that the spectra are split into that the resonance lines are further split into final lines. And why is this happening? This is because of spin coupling. And what is this spin coupling? It means that the proton of one group is coupled to the proton of another group, and this is called spin coupling, and it is also known as J coupling. J coupling, and why? How does this occur? This occurs due to an interaction mediated by the electrons in the intervening bonds. So as we saw that this CH3 group is connected to the CH2 group through a bond. And what is this bond? This bond is actually formed by the sharing of electrons between them. And so so these two group the nuclear this nuclear and this nuclear are coupled through the intervening bond between the two groups. Okay, so this takes place when a nuclear spin polarizes a nearby electron spin, which then polarizes its partner electron. This polarization is passed on to the neighboring nucleus, continuing as long as the spin order is maintained. Okay, so the nucleus. So as we had seen that the nucleus is surrounded by an electronic cloud, right? Is surrounded by an electronic cloud. And this nuclear spin polarizes the electron, surrounding electron, and this polarization is transferred to the, and the polarization of this electron is transferred to the neighboring nuclei, and in this way this gets transferred from one bond to the other bond. So it depends on the, so as we see that it depends on the nature of the bond. So what type of bonds are there, single bond, double bond, and it also depends on the nature of intervening atoms in the bonding sequence. So whether it is a methyl group, or it is a methylene group, or whether it is a hydroxyl group. So what type of atoms are present, that will also determine the spin coupling. Okay. So the spin coupling can extend up to 4 to 5 bonds. The coupling interaction between two spins I1 and I2 is quantitatively given as J12 I1 into I2, where J12 is called the coupling constant. Okay, so what is shown in this figure is that, yeah. So what does this figure show? So consider there are two spin. One is spin A. There are two nuclei. Okay. So consider that there are two nuclei. One is a nuclei named X, and another nuclei is named A, and another nuclei is X. Now this nuclei A can exist in two states. So when this nuclei will be placed in magnetic field, it can exist in the presence of magnetic field. There is splitting of energy, and this nuclear spin can exist in either the alpha state or in the beta state. Now, similarly, this X also can exist it can also exist in alpha state and the beta state. Now, depending on whether this X is present in the alpha state or the beta state, this causes further splitting, or this will control how the how the nuclei of A will behave. Okay, so if the suppose this, so you can see that this spin X can be either be present in the alpha state or the beta state. So if spin A is, if the nuclei A is present in alpha state and nuclei X is present in alpha state, there will be it will absorb a different energy. And if this nuclei A is present in alpha state and X is present in beta state, then it will absorb another energy. And because of this, we see there are there is a splitting of that this single line is now splitted into two separate lines. So, so what is so as we had seen that the coupling interaction is given by J12 I1 to I2, and J12 is called the coupling constant. So this is actually called the coupling constant. So coupling constant, what does this value tell us? This value shows us that what is the strength of interaction between the two nuclei. So the strength of coupling is called the coupling constant, and it is denoted by the symbol Nj. So what does Nj stands for? So N is the number of bonds, or the number of bonds through which one nuclei is connected to the other nuclei. Okay, so discuss some examples about this. So so suppose there is one nuclei here, and it is connected to, suppose suppose this one will be. So this proton is coupled to this proton through three bonds, right? 1, 2, and 3. So that is what N stands for. Okay. So one bond coupling constants are for the are the heteronuclear. So the what are there are so there can be homonuclear. So like C13H1, these are heteronuclear coupling. C13 is one nuclei, it is coupled to proton, or N nuclei is coupled to proton. So these are called the heteronuclear coupling. So heteronuclear coupling always have a higher coupling constant value. So the J12 value is higher for heteronuclear system than as compared to the homonuclear system. So as you can see that the H1C13 coupling constant gives a range of around 100 to 250. And these homonuclear, that proton-proton coupling has a lower value, 5 to 20. Okay, so what is shown in this figure? It shows that the A nuclei can be present in the alpha state, and it is showing what type of transitions are possible. So depending on whether the X nuclei is in beta state or alpha state. So if it is in beta state, then the frequency of absorption of energy will correspond to nu A1. If the beta, if the X nuclei is in alpha state and the A nuclei is in beta state, then this will correspond to this frequency. And if the X nuclei is in alpha state and the A nuclei is in alpha state, this will correspond to this absorption of this frequency. Okay. So we will understand the concept. We can understand if we I'll solve this question. Let's solve this question to understand the concept better. So what is asked in this question is how many peaks would a 1D 13C spectrum of 50% deuterated chloroform have? Okay. So everyone knows the formula of chloroform. So it is CHCl3. Okay. Now it has been said in the question that in this chloroform molecule, 50% of the chloroform are deuterated. 50% are deuterated. So what does it mean? It means that 50% of the molecule exists as CHCl3 and the rest 50% exists as CdCl3. Okay, now you have to determine the number of peaks that you would obtain for a deuterated 50 for a 50% deuterated chloroform. So for this system, so 50% chloroform existing in the form of CHCl3 and 50% existing in the form of CdCl3. And for this case, you have to determine that how many peaks you will observe if you record a NMR spectra. So how does the structure of this chloroform look like? We'll have Cl, and this will have a structure. Okay, now how do you calculate the number of peaks? So the number of peaks so the splitting of peaks is given by the formula Ni plus 1, right? 2Ni plus 1, where what is N? N is the it is the number of protons, number of equivalent protons, and I is the spin quantum number of that nuclei. Okay, spin quantum number of the nuclei that we are considering, and N is the number of equivalent protons, that is or the number of nuclei that is present for the number of nuclei corresponding to the spectra that we are recording. So if we consider this CHCl3, this CHCl3 has only one proton, and the spin quantum number of a proton is half, right? So the number of peaks that we will obtain for CHCl3 will be 2, right? And now if we consider the CdCl3 molecule, it will split into the number of peaks that we will obtain for CdCl3 will be 2n I2 plus 1. Okay, 2n I2 plus 1. There is only one deuterium nuclei. So 1 and I2. What is the spin quantum number of deuterium? It is half. It is 1. It is 1. So we had discussed what will the spin quantum number for different nuclei in our first lecture. So the spin quantum number for deuterium is 1. And so the number of peaks that we will obtain for CdCl3 will be 3. will be 3. So this will lead to a total number of peaks that we will obtain will be 5. Okay. So is this question clear?
Yes, clear. But can you um, repeat your concept about the spin quantum?
Spin quantum number.
Yes, here.
Yes, so spin quantum number, I had discussed that. So depending on its mass number and the and its atomic number. So like proton, proton, carbon 13, these all have a spin quantum number of half. H1, C13, N15, these all have spin quantum number 1.
1.
Okay. Then deuterium N14, N14, these have spin quantum number of 1. Okay. So so you have for the common nuclei that are used in NMR, you need to remember the spin quantum number. There is a method to calculate the spin quantum number, but it is better if you can remember the spin quantum number of few common nuclei which are used in NMR for recording the NMR spectra. Okay. So you remember that the spin quantum number of deuterium is 1. Okay. So that is why here the I value is 1. And this, as a result, the number of peaks that we obtain for CDCl3 will be 3. So
Thank you. Actually, I forgot the concept. Now it will revised for me. Thank you.
okay. It is clear, right?
Yes, clear.
So what is the concept that I discussed just now? So you remember the concept that the resonance line of a nucleus J coupled to an equivalent nuclei of another type gets split into 2n+1 lines, where I is the spin of individual nucleus in the equivalent group. Okay, so the resonance line of a nucleus. So here we are which nucleus we are considering? We are considering the proton. We are considering the proton. Okay, so this proton is an equivalent coupled to n equivalent nuclei of another type gets split into 2n+1 lines. So here, this proton is coupled to C, and there is only one proton. This is NMR active. This C is actually C12. So what will happen? So here n is 1 and I is half. Now, if the nucleus is J coupled to two groups of equivalent nuclei having n and m nuclei, and if their spins are I1 and I2, then the total number of lines will be 2n+1 and 2m+1. Okay, so this concept is not required for this question because here what we see that this deuterium is coupled to only one nuclei. It is not coupled to two different nuclei. So just you can apply this formula 2ni+1. But if in case this was coupled to another nuclei, a different nuclei, then we would have 2n+1. This is actually 2n+1 into 2m+1. So these many number of peaks we will observe when we record the spectra. Okay, so 50% deuterated chloroform means there are 50% chloroform molecules that will exist as CHCl3, and 50% will exist as CDCl3. And so the number of peaks that will obtain for CHCl3 will be 2, and the number of peaks that we will obtain for CDCl3 will be 3, and so the total number of peaks will be 5. Okay. So moving to the next question, the proton spectrum of a 25% C13 labeled CH3COD will have. Okay, so here in this question, so this is CH3COD. So there are 75% of the molecules. So if there are 100 molecules of the CH3COOD, then 75 molecules will have C12, will be C12 labeled. Okay. So 75 molecules will be in this form, and other 25 molecules will exist in C13. C13 labeled CH3COOD form. So 25 molecules will have these where the C carbon is C13 labeled, and there will be 75 molecules where the carbon is C12 labeled. Now you are recording the spectra of such a molecule, or of such a sample where 75 molecules exist in this form and 25 molecules exist in the C13 labeled form. So what will be the proton spectra that you will obtain? So that you have to find out. So, so can you think and try to, so this question was there in week 2. So could anyone solve this question? So if you have not solved this question, you can try it now. So you can, I will give you 2 minutes and then I will discuss this question. So you read the question once again, and then we can take up the question. So remember that the C12 is NMR inactive, while C13 is NMR active. So now depending on whether this proton is coupled to C12 or whether it is coupled to C13, that will decide the number of peaks, or the splitting of peaks will be based on whether this proton is coupled to this C12 or whether it is coupled to C13. Okay. So just now what I said, how do you calculate the number of peaks? So you apply the formula 2ni 1 plus I1 plus 1. So that is the formula that you have to apply, right? N is the number of equivalent protons. Okay. So you are recording a proton spectra. So you have to consider the proton nuclei, right? You're not recording the C13 spectra, you are recording the proton spectra. So you have to say for, so in this case, N is the number of proton that you have to consider. So in this case, what happens if it is C12, if it is C12, so what I had said in the last slide, that N is the J coupled to N equivalent nuclei. Okay. Now in this case, CH3COOD, all these protons are equivalent. All these protons are equivalent. So N will be 1 in this case. Okay. N will be 1 in this case, but I1, but here carbon 12, the C12 has spin quantum number 0. Okay. So you will obtain only 1 peak for CH3COOD. Okay. There will be only 1 peak that you will obtain for C12 labeled CH3COOD. Deuterated acetic acid. So, not deuterated. But in this case, since this is C13 labeled, the number of peaks that you will obtain will be. So here these 3 protons will be non-equivalent, and what you will get is 2 into 3 into half. So C13 has a spin quantum number half. right? Plus 1, and this will give you how many peaks? 4 peaks. This will give you 4 peaks. Now these 4 peaks will be in the ratio of 1:3 to 3:1. What will be the ratio of their intensity? One is to 3:1. Okay. Now, when you are recording the proton spectra, this spectra will merge with this spectra. So there will be overlap between these two spectra, and these the central two peaks that you obtain, that will merge and it will give a single peak. It will give a single peak which will have an intensity 3 plus 3. You will get a peak of intensity 1:6:1. Okay, because both these molecules are present. So in the sample, you have both this C13 labeled compound and C12 labeled compound. So the spectra that you will obtain for this CH3COD, C13 labeled compound and C12 compound labeled compound will overlap with each other, and this central peak will merge, and we will get 3 peaks of the intensity. 1:6:1, because C12, as you can see, that C12 is in mode number, right? It is 75%. The percentage of C12 that is compound present is 75%. So the intensity of this peak will be much higher than the intensity of 25% C13 labeled C3COOD. So as a result, when these two spectra will merge, we will get a spectra which will look just like this. So three peaks which are having an intensity in the ratio 1:6:1. Okay. So we will look at the solution once more to understand it more better.
Hello, my question is
Yeah.
here ki uh, carbon 12 is inactive for the NMR, okay?
Yeah.
Then why are you considering these peaks? According to the formula, I got one peak from here, okay na?
Yeah.
Uh,
You got one
but
peak here. Yeah. Tell me.
then why we are considering this peak? Because this one is the NMR inactive na?
Yeah, this is NMR inactive. C12 is NMR inactive. So if we were recording a C12 spectra, then we would not have got any peaks. C12 spectra, if we record C12 spectra, then we will not get any peak. But we are recording proton spectra. So since we are recording proton spectra, so we will get one peak for for
Okay,
this proton.
okay,
Okay, for this
hydro.
proton, we will get only one peak. Okay, and this proton is coupled to C12. Okay, so that is why the value of I in this case was,
One.
so when we use this formula 2A and I1 plus 1, the value of I1 was 0. The value of I1 was 0, and so this is 1 and this is 0. So the number of peaks that we obtained was 1. However, in this case, the this is C13, right? So the value of spin quantum number for C13 is half. And these protons are in a different chemical environment. So these protons are non-equivalent. So that is why we now n in this case is 3. Okay. So we will look at the solution once again to understand the concept better. So 75% of C3COOD will be C12 labeled. Okay, for C12 labeled C3COD, the number of peaks obtained will be singlet. So, yeah. So for the C13 labeled compound, we will obtain only a single peak. So that single peak is called singlet, right? This is because for carbon 12 labeled compound, I is equal to 0 for C12, and so here when we applied this formula, we got the we got the value 1. Now for 25% of the molecules, but there are also 25% molecules which are existing in the C13 labeled form. So for the C13 labeled form, the number of peaks will be how many? It will be 3. Okay. And these 3 peaks will have an intensity ratio 1:3:3:1. Now the quartet is weaker. The quartet is weaker. Why? Because there are only 25 molecules of it. So the quartet is weaker while the singlet is stronger. And when these two merge, so the quartet will overlap with the singlet, and this results in a much stronger central peak that produces peak intensity in the ratio 1:6:1. So the correct answer for this question was option 3. So this peak merges with this peak, and the result of this is a much larger central peak. Okay. Obtained a much larger central peak and two shorter peripheral peaks. And the ratio is they are in the ratio 1:6:1. Okay. Is this concept clear? Good to.
Yes, yes, clear.
Okay. Now another question that was asked in week 2 was the proton spectra of vinyl chloride will consist of. So this is vinyl chloride, CH double bond CH Cl. Okay. So for solving these type of questions, what you have to look for is how many, whether the protons that are present in this compound, whether they're equivalent or non-equivalent, and how will you decide whether these protons are equivalent or non-equivalent? So the protons which are in the same chemical environment, they will be equivalent, and the protons which are in a different chemical environment, they will be considered non-equivalent. Now this compound has how many protons? This has 3 protons,
2.
right? 1, 2, and 3. Okay. Now, if you look at the chemical environment, so let us label these protons. Okay, this is A, this is B, this is C. Now, if we let us first consider the HA proton. Okay. The HA proton, what is the chemical environment of HA? So this HA is surrounded by a proton, this proton, HB proton. Okay. In its chamber, it has an HB proton, and there is another proton that is in a cis position. This HA proton, HA, this HC proton is in cis configuration to the HA proton, right? So HA and HC are in cis position to each other. Well, if we consider this HB proton, so on one side it has this HA proton while it is in trans to the HC proton. It is in trans position with respect to the HC proton. So if you, so this I have this representation of the structure is in 2D, but you have to imagine it in a 3D configuration or 3D geometry. So basically this carbon are sp2 hybridized, right? So this is present in a plane. This is present in a plane, and above the plane there is one proton. Below the plane there is one proton. So this carbon is present on the plane. These carbon atoms are present on the plane, and above the plane there is one proton. Below the plane there is one other proton. Similarly, for the second carbon, one proton is present below the plane and one proton is present above the plane. So now, if we look at the chemical environment of this proton has a chlorine group near to it, right? And below the plane it has another proton. Okay. Now, if we look at this proton, consider this proton. This proton has a different chemical environment. It is surrounded by chlorine atom, and opposite to that, or in a trans position, it is coupled to another proton. So all these protons are in different chemical environment, right? They are not in. So last class I had given you the example of ethane. So if you consider the example of ethane, CH3, 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 CH3. So now this proton, if you consider each proton one by one in case of ethane. So in case of ethane, this proton has also how many protons surrounding to it? 1, 2, 3, 4, 5. This proton has also protons surrounding it. There are no other atoms surrounding it, right? So all these protons are equivalent. Why are they equivalent? Because if you look at their chemical environment, they are all these for each of these protons have the same chemical environment around them. But in this case, all these protons are in a different chemical environment. So these protons are non-equivalent protons. Okay. Now in case of non-equivalent protons, the concept of 2n I plus 1 that does not 2n I plus 1, this formula does not hold true for this non-equivalent proton. So what concept do we have to apply for these type of protons? So now what you have to do is, so
Uh,
did you understand what I'm trying to say? So so this formula is actually this here n stands for the number of equivalent protons in the neighboring atom. Number of equivalent protons in the neighboring atom, right? In the neighboring atom. But here there are no equivalent protons. All these protons are non-equivalent. So we cannot apply this formula directly. Okay. So what we have to do? So we have to consider each proton one by one. We have to consider each proton one by one. So first we will consider the HN nuclei. Okay. So this HN nuclei, it has one proton in its neighbor, which is bonded to this carbon. So this is one, this is two. This is carbon one. So because of this proton, Hb proton will cause splitting of the Ha proton into two, will cause the splitting of Ha into two different peaks. Okay. So if you apply the n plus 1 formula, so now so what we did was that here you have to consider each proton separately. Okay. So once you have to consider, first we have to consider that this HA is only coupled to, do not look at the HC proton. Look at only the HB proton. This is coupled to HB proton. This HB proton will cause splitting of this HA proton into two peaks. Okay. So this is called the JAB. Called the JAB. Now this JAB, this will again further be split into two more peaks by JC. So this will again be split into this peak will again be split into two more peaks due to coupling with the HC proton. This is called JAC. This is called JAC. So what do we obtain finally? Finally, we obtain doublet of doublets. So here we obtain. So first there were two doublets. Okay. And now this doublet is again further split into two more doublets. So that is why we get what doublet of doublets. So, so let's look at the solution to understand it better. Okay. So this is an example of complex coupling. In this case, a proton is coupled to two or more sets of. So if you consider a proton, this proton is coupled to two or more sets of non-equivalent protons. So if we look at AHA, this AHA is coupled to two different non-equivalent protons. This Hb and Hc are non-equivalent. Okay. And so in this case, what we have to do? So HA is coupled to both Hb and Hc, but with two different coupling constants. So the coupling between Hb and HA and the coupling between HA and Hc is different. So because of this, and why is it different? This is different because the Hc or According to this, if we see this figure, this HC is in cis configuration. Okay, is in cis to HA across the double bond and splits the HA signal into a doublet. So this HC will split the HA into doublet. Okay, so you can also understand it in this way. So this is actually a concept of diastereotopic proton. Diastereotopic proton. This is called. This concept is called. So this is in cis to each across the double bond and it splits the HA signal into a doublet. The HA doublet subpic is split again by HB into two more doublets. Into two more. This is geminal coupling. So because what is this geminal coupling means that this proton is on the two sides of the double bond. This pattern is referred to as a doublet of doublets. So in a similar manner, if we look at HB, now this HB will also be split into this HB is coupled to HA. This HA will first split the HB into two different peaks, into two peaks. That is called doublet. And then this doublet will again be split into two more doublets by HC. Okay. Now, similarly for HC also, if we look at the spectra of HC, this HC will also be will first be split by HA into two peaks, and then the HB will again split this two peaks into two two more peaks. So this is called doublet of doublet. Okay.
Hello. You are not audible to me.
Hello. So sorry, there was a power cut in my area, so I got disconnected. I will start the session once again. Sorry. Yeah. So yeah, we were discussing this question. So what will the proton spectra of vinyl chloride? Okay. So let's start. Yeah. So in this case, as we can see, that there are no plane of symmetry in this molecule. First of all, there is no plane of symmetry. There is no plane of symmetry in this molecule, and since there are these are non-equivalent protons, so this proton is in cis to this Hc proton, and this Hb proton is in trans to this Hc proton. So all these protons are in different chemical environment, and because of this, we have to consider each of the protons separately. So first, this proton, which will be split by Hc into two different peaks, and then this peak will be further splitted into two more peaks by Hb. So that results in the formation of doublet of doublets. And in the case of doublet, what happens that the ratio of the intensity that we were observing for equivalent protons, it will come in the ratio of 1:2:1, 1:3:3:1. This ratio is not followed in case of this in these cases, and so what we obtain is all these intensities have roughly the same have the same intensity, 1:1:1. So if it is doublet of doublet, all these peaks will have the same intensity. Okay. So basically, how will the spectra look like then for vinyl chloride? So it's not working. This one is not working. So basically, this peak spectra will look like. So first, we will get three different peaks. We will get three different peaks. One is for the Hc. So this proton, this Hc proton is coupled to the chlorine. So it will show the highest chemical shift. Okay. Now this proton is split into two more peaks. Doublet of doublet means we will find two finer peaks. Basically, just 1 second. What we will see is that it will have two peaks. This is for Hc, for Hb, for Hb. This will also have a this will also show a peak, but it will be near to the this will show a lesser chemical shift. Okay. Then we will get another peak for HA. So in this way, somewhat it will look like this. So this is called doublet of doublets. So there will be three peaks, and these three peaks will be further splitted into these three peaks will be further splitted into finer peaks, and this is called the doublet of doublets. Okay. Now consider another case. This is another case of BrCH2, CH2, CH2, Cl. So in this case also, if we look at the protons, so for this compounds, let's first look at the protons. Okay. So this is the compound that is given to us, and if we look at the protons, then how many protons does it have? 1, 2, 3, 4, 5, 6. Now these protons are the protons that are bonded to carbon and bromine. They are equivalent, right? They are equivalent. But these protons, if you look at these protons, so one of this proton has a neighboring proton in its surrounding. Has two neighboring protons in its surrounding, while the Hb proton has a bromine in its surrounding and another proton in its surrounding. So this proton, this pro- the, so the, this These protons, these two protons are different. Okay. Now, moving to this third proton, this proton which is bonded to carbon and Cl. So these two protons are equivalent, but this proton is different the the Hb proton. Okay, because this Hc proton has a chlorine in its environment, while this proton has two protons in its environment. So what we will find that we will observe we will obtain three different peaks. Now, if we see the multiplicity or what will be the further splitting of these peaks, if we want to calculate what will be the further splitting of these peaks. Now, here again, the concept of this n plus 1 will not apply. And what we will have to do in this case is we have to consider one by each proton one by one. So if we look at the Hb proton, this Hb proton has, so it will be split by these protons into, so there are two protons. So this HA proton will split it into how many peaks? 2 plus 1 equal to 3. This HB will be splitted into a triplet. First, it will be splitted into a triplet because there are two protons. Now, this is called so why is this happening? This is happening because the coupling between HA and HB is different from the coupling between HB and HC. So that is why we cannot directly do this. We cannot directly add these two protons and these two protons, this proton. So we cannot do 2 plus 2, 4 plus 1. So this is wrong. If you do so if you look at proton and if you look at the number of protons in its neighboring atom, then the number of protons in its neighboring atom are how many protons are there in its neighboring atoms? There are four protons. But if you apply this, if you put n equal to 4 in this case, this will be wrong. Okay, because these two protons are not equivalent. They are non-equivalent. So in this case, you have to consider first this environment, these protons. Because of these protons, what is the splitting of Hb? Then next you have to consider these two protons, and because of these two protons, what is the splitting? Okay, so first we are considering the splitting of Hb because of HA proton. So this HA proton, there are two protons, and this HA proton will split the Hb proton into three different pieces, triplet. Now these three will again split into three more because of its coupling to HC. Okay, so there will be splitted into three more peaks. Okay, so this is called triplet of triplets. So first it was splitted into three peaks, and then this three peaks are further splitted into three more peaks. So this is what is this is called triplet of triplets. Triplet of triplets. Okay, but if you look at the case of HA, now if you calculate what will be the spectra for HA, what will be the splitting? So HA has HB in its neighboring HB proton in its neighboring environment, or this proton. This HA proton is bonded to carbon, and the adjacent atom which is present to this carbon is this carbon. This carbon has two protons, and because of this, the number of what will be the water? How many protons are there in its neighboring atom? Two. So n will be 2. So this HA peak will be split into triplet. Okay, this will follow the normal rule that we use for equivalent carbons, right? Equivalent protons. But in this case, this HB is in two is in an environment which has two different protons. So for these case, we have to consider it in a separate manner. Okay. Similarly, for HC also, we will get triplet because this HC has this HB proton in its neighbor. So there are two HB protons. So this HC peak will be split into three peaks. Okay, 2 plus 1 equal to 3. So for HC, so if you see the spectra, so what we will see that this HC is split there are three peaks, three main peaks for HC, HB, and HB. Now this HC peak is further splitted into three finer peaks. The HB is sorry, 1 second. This is so HA we will get triplet. So this figure is actually wrong. Do not look at this figure. So HA will be a triplet. Okay. So chlorine is more electronegative, right? Since chlorine is more electronegative, this protein is more de-shielded, and because it is more de-shielded, we will obtain a peak for HC at a higher chemical shift. At a higher chemical shift, so these will have, it will come like this. This is for HC. Okay. Now bromine. Bromine is less electronegative, so it will also be de-shielded, but to a lesser extent. So we will obtain a triplet for HB also, just in this manner. And but for HB, what will be the case? It is triplet of triplets. So there will be, it will divide it into finer peaks. So 3 peaks, and again 3 peaks. 3 peaks means there will be total 9 peaks that you will obtain. 1, 2, 3, 4, 5, 6, 7, 8, 9 finer peaks you will obtain for this HB proton. If you magnify this peak, you will obtain that there are actually 4 peaks that is making up this the peak for HB. Okay, so there will be 9 peaks that will be for HB. Okay, so you have to I hope this concept is clear, and so whenever these type of questions are asked, you have to first look at how many protons are present and whether these protons are equivalent. What is the surrounding of so you have to look at first you have to look at how many protons, and then you have to take up each proton separately and check the chemical environment of each proton, whether this proton has an equivalent proton in its surrounding or whether the proton has a non-equivalent proton in its surrounding. And based on that, you have to solve this question. Okay. Yeah. So I had shown this table in the last lecture also. So try to have a rough idea of the what is the chemical shift value for these different groups. So for methyl group, you have a chemical shift at a range of around 0.7 to 1.3. For this methylene protons, there it has a higher chemical shift, 1.2 to 1.4. So like this was also there in the lecture slides. So if you can remember this figure, if you can have a rough idea of this figure, then it becomes easier to understand what is the chemical formula of the, or what is the chemical structure of the compound given the formula. So why I showed this slide is because I wanted you to solve this question. So these type of questions have been solved in the lecture also. So what you have to do in this question is that the molecular formula, I hope everyone is with me.
Yes.
Yes, yes. Okay. Okay. So, Muthu, are you following what I'm telling?
Sorry.
Okay.
Speak
So,
again.
yeah, are you able to follow what I'm saying? Hmm. Okay. So we will look at this question. We will look at this question. So in this question, the chemical formula is given C3H8O, and what you have to find out that what will be the structure of this compound. What will be the structure of the compound, and based on the given information. So we have been given some certain information. So based on these information, you have to deduce the structure of the compound. Okay. So what is given in this table? This table shows that table shows that there is a, so you have recorded the NMR spectra. You have the data for the NMR spectra. So you have obtained a chemical shift at 1.1 ppm, 1.1 ppm, which is a doublet. Okay, which is a doublet. Doublet means how will the spectra look like?
Two
Yeah,
spectrum.
2 peaks. It will have 2 peaks. So there are 2 peaks at 1.1 ppm, and if you do the integral of these peaks, this is coming because of 6 protons. Okay. Now, what other information is present? At 3.9 ppm, you have a septate. Septate means
Seven.
there are yeah, there are 7 peaks. Okay, 7 peaks. So yeah, it will look like something like this. And what will be the ratio? Intensity ratio. What will be the value of the intensity ratio? You remember the Pascal's triangle? 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Then it will be 1, 5, 10, 10, 5, 1. So in case of 7, if there are 7 peaks, the intensity ratio will be what? It will be 1, 6, 15, 20, then 15, 6, 1. So if you get a septate, then the ratio of their intensity will be 1 is to 6 is to, so it will be like this. 1, 6, 15, 20, then again 15, 6, just a second, sorry. Yeah, yeah. So what I was saying, 1, then 6. So it will come in this ratio. Okay. So the first peak will have a shorter intensity. Then as we go along, it will increase to a particular intensity, and then again it will decrease. So you have a septate at 3.9 ppm. Then you have a singlet at 4.8 ppm. Okay. 4.5, 80 ppm, you have a singlet. Now, based on these information, you have to tell what will be the structure of the compound. Now, how do we solve these questions? So you have to first calculate the double bond equivalent of these compound. So what is the formula for double bond equivalent? So the formula, this was discussed in lecture number 10. So if you remember the formula, so this is the formula for double bond equivalent. So if a compound C minus H by 2 plus N by 2 plus 1. Okay. So this is the formula for double bond equivalent. So how many carbon are there in this compound? There are 3 carbon, right? There are 3 carbon. So you put 3 in this in place of carbon. How many protons are there? 8. There are 8 protons. 8 by 2. Now, are there any nitrogen in this compound? There are no nitrogen. So you put the value 0 and then plus 1. So this gives us a double bond equivalent equal to 0. What does this mean? Why do we calculate the double bond equivalent? So double bond equivalent helps us to understand whether this compound has any double bond or not, whether this compound has any pi bond, or whether there is an aromatic group, aromatic ring in that compound. So since the double bond equivalent is 0, it means that that it is a saturated compound. It is a saturated compound. It does not have any double bonds, any pi bond. Okay. Now first, what is the first information that is provided? That at 1.1 ppm, you have a doublet. So how do we get doublet? So it can be present because of, so if you look at this compound, so it can be, so there are 6 protons. So there are 6 protons. It means that because of this proton, because of this because so if so if the structure of this compound is like this, then what will happen? These protons, CH3 protons, the CH3 protons will be split into doublets. This CH3 protons will be split into doublets. Why? Because the number of protons in the adjacent carbon is 1. Okay, number of protons is 1, n equal to 1. So n plus 1 will be what? 1 plus 1, 2. So because of this proton, this CH proton will split the CH3 protons into 2 peaks, doublets, and that is why we are getting a 1.1. So 1.1 ppm means it is because of the CH3 groups. Okay. 1 point, I showed you the table, right? This table. So 1.1 ppm means this the peak that you are getting is because of a methyl proton. Is because of a methyl proton. But you are getting 6 proton, but this intensity is because of 6 proton. This means that this compound can exist in this form. Okay. Next information is given that you are getting a ppm at 3.9 value. So this means, and this is because only of one proton. So one proton means these protons are present is causing the splitting of this CH proton into septate. So are you able to understand? So look at this compound CH3. This is CH. Okay. Now first we were looking at this proton. This proton has only one proton in its neighboring atom. Okay. This proton has only one proton in its neighboring atom. So it is split into 7 different peaks. Okay, 6 plus 1. N plus 1, N you have to put what? Yeah, and you have to put here 6. So 6 plus 1 equal to 7. Now we are looking at this. So sorry. N is equal to 1. Right, N is equal to 1. 1 plus 1 equal to 2. So first we were looking at this proton. This proton, these proton A, HA, HA. HA will be equal to 2 plus. So for HA you are getting a doublet. You are getting a doublet, right? You are getting a doublet. So why you are getting a doublet? Because in its neighboring, the neighboring atom has only one proton, and because of one proton, it will be split into 1 plus 1, that is 2 peaks. So that is a doublet. Now you have to consider this proton. Now this proton has in its surrounding 6 protons. This proton has 6 protons in its surrounding. So when you apply this n plus 1 formula, here n will be what? N is the number of neighboring protons, number of protons which are present in the neighboring atom. So n will be 6 and 6 plus 1 will be 7. So that is why this peak is further split into finer peaks, finer 7 peaks. Okay. Now moving to the third information. So 4.8. So if you look at 4.8 ppm, 4.8 ppm is for which group? So it can be this group, or it can be this one also. So, but there is no F. So let's check. Now you are getting a singlet in this case, and you are getting a chemical shift at 4.8 value. So one proton exchangeable with D2O, and because of this, we are getting a singlet. One H is deshielded, having no adjacent proton. It may be HXH. So since the proton is exchangeable with D2O, so it may be HO and another compound. So the possible structure of this compound is this one. Okay. So this proton it was actually bonded to the oxygen, was bonded to the electronegative atom, and because of this, this proton is actually exchangeable. This proton is exchangeable, and so here one more information is here one more information over here that is given is this proton is exchangeable with D2O. So which proton is exchangeable with D2O? It is usually the proton which is bonded to oxygen or any electronegative atom. If a proton is bonded to any electronegative atom, then it is exchangeable with the solvent. So that is why this proton is bonded to oxygen. So this is the chemical structure of the given compound. Okay. So I hope this is clear. So there are 3 different protons. Okay, 3 different protons. So first we look at the HA protons. So the HA protons has HB in its surroundings. So this HF proton is split into a doublet. 1 plus 1, we get a doublet for HA proton. For HB proton, what do we get? We get a septate, because this HB proton is surrounded by 3 plus 3, 6 protons, 6 equivalent protons. So here we put n equal to 6 and we get 7. For HC, there are this is bonded to oxygen. This is bonded to oxygen, and this is exchangeable. So we get only a singlet in this case. We get only a singlet, and the shift is at around 4.8 ppm. Okay. So we will move to the next question. So another question is C7H8O. This is similar to the previous question. So in this question also, you have to first find out the double bond equivalent. What is the formula for double bond equivalent? So you apply the formula C minus H by 2 plus N by 2 plus 1. C minus H by 2 plus N by 2 plus 1. Okay. So number of carbon in this compound is 7. The number of protons are 8 by 2, and number of nitrogen 0. And so if you apply this formula, we get 4 double bond equivalent. 4 double bond equivalent, it means that there can be many possibilities. So it has 4 double bonds. So it can be that there are 3 double bond and 1 ring, or it can be 2 double bond, two double bond and 1 triple bond. That is also possible. Okay, so there can be many possibilities. Now looking now after this information, we have to also look at the value of chemical shift. Okay. So if you look at the values, if you look at the value, this 7.2 ppm indicates that there must be a ring, or there must be an aromatic proton present. That is why we are getting a chemical shift at 7.2 ppm. So that is why I was saying that you need to have a rough estimate of what are the values of chemical shift for different groups. Okay, so first we are 3.3 ppm. So the 3.3 ppm means what? And we are getting a singlet. We are getting a singlet means there are no adjacent proton at the neighboring position, and the protons are de-shielded. Okay, so it can be this one, CH3, and this CH3 proton does not have any neighboring proton in its surrounding. It does not have any neighboring proton in its surrounding. So there will only be a single peak. There will be no splitting of peaks because it does not have a proton in its surrounding. Next information that we have is it has a chemical shift of 6.85. Now 6.85, and we get multiplet. And the intensity is because of 3 protons. Intensity is because of 3 protons. So it can be what? So it can be the 3 protons are adjacent to multiple proton at neighboring position, and the protons are de-shielded. De-shielded. That is why we are getting a very high chemical shift value. And so this can be like this. This protons can be a part of the aromatic ring. Okay, so that is why we are getting a chemical shift of 6.85. Now 7.2 chemical shift, and what is the information provided? That is a triplet. It is a triplet, and it has 2 protons in its adjacent. Okay, 2 protons in its. The intensity is because of 2 protons, so it may be these protons, the protons that are present in the meta position. Okay. Protons which are present in the meta position with respect to this group. Is it clear? So based on this, the chemical formula or the structure of this compound can be this one. It can be it will have a structure. It will have this structure. Okay. So you have to practice these questions to get an understanding how you can approach these questions. So the chemical shift, first you have to know, you have to have a rough understanding of which groups have what chemical shift, and based on these intensities, how many protons are involved. You can. So since there was 3 protons and you were getting a singlet, it means that it is not bonded to any. It is not bonded to any adjacent carbon which are having protons. That is why it is CH3. Okay, and then the second intensity you are getting because of 3 protons. So these may be the 3 protons that are in ortho and para position. And then you are getting another chemical shift at 7.2 ppm. That is because of two protons. So these two protons may be the one because of which you are getting this chemical shift. And when you combine all these three information, you can get the structure of the chemical compound, and this is the structure will be this one. Okay. Now, another question which was asked is which of the following commutation relationship is correct? Now, this concept was discussed in the quantum mechanical principle of principle of N- principles of NMR spectra. So, so what does commutation relationship mean? So, the angular momentum can have three different components: Ix, I1, Iy, and Iz. Ix, Iy, and Iz. So Ix is the angular momentum vector along the x direction, Iy angular momentum vector along the y direction, and Iz is the angular momentum vector along the z direction. Okay, and the rule or the principle that is followed when we deal with these operators are that if Ix and Iy will be equal to Iz, so it follows a cyclic relationship. Cyclic relationship means x and y will give you z, z and x will give you y, y and z will give you x. Similar way, x and z will give you minus y, z and y will give you minus x. Okay, so that is what is meant. It follows a, remember, what do you have to remember here is that the commutation relationship follows a cyclic order. Follows a cyclic order. It means that x to y to z, x to y to z. So Ix and Iy will give you what? Ix and Iy will give you Iz, I, Ix and Iy. No, it will not give you. This is wrong. This option is wrong. Ix and Iz, Ix and Iz. If we go Ix and Iz, that will give you minus Iy. This will be minus Iy and not, this will be not, this is wrong. This is wrong. This will be minus Iy. And if we do Iy and Iz, we will get positive Ix. So this option is also wrong. So the only correct option in this question is option number A. Okay. So we'll look at the solution. So there are three operators, Ix, Iy, Iz, and these three operators correspond to the components of the angular momentum along the x, y, and z axis. Along the x, y, and z axis, the fundamental commutation relations for angular momentum operators are Ix, Iy will give you Iz, Iy, Iz is equal to Ix, Ix will give you Iy. So these relationships are cyclic. Are cyclic meaning the order of the operators is important. So what is the order of the operator, that is important, and they follow the pattern x, y, z. Okay. So just remember that it follows the cyclic relationship. Yeah, good to what is your question?
Yeah, my question is where is the application of this formula in the communication relation?
So this is required for, so in case of strongly coupled spin system. So when we consider the spectra of strongly coupled spin system, then we have to apply the we have to apply the quantum mechanical principles, and there are a lot of calculations that has to be done following these principles, which gives you what will be the intensity, what will be the chemical shift. So those for strongly coupled spin system, we have to use these concepts. So we will discuss what is strongly coupled and coupled spin system in the subsequent slides. So, but for now, you remember that this follows a cyclic order. Cyclic order means x into y will give you z. But if you do x into z, this will give you minus y. Similarly, z into y will give you minus x. Okay. So it is moving from x to z, x to y to z. So what is the concept of flip angle? So there is a question based on flip angle. So what happens in NMR when we record an NMR spectra? So mainly in Fourier transform NMR spectroscopy, and RF pulse is applied. What is an RF pulse? An RF pulse is a radio frequency which is applied for a very short time, tau, which is applied for a very short time, tau, and this the time duration for which this RF pulse is applied is of the order of a few microseconds. And the duration for which this radio frequency is applied will actually help to cover a range of megahertz or at least several kilohertz range of frequencies with similar amplitude will be generated around the central frequency omega naught. So as you can see in this figure, so we have a sample. Okay, we have a sample, any sample, and we want to record the NMR spectra of that sample. So what we do is we apply a short radio frequency pulse. And what is this radio frequency pulse? The radio frequency pulse is basically an electromagnetic radiation of having an energy equivalent to radio frequency, and this radio frequency is applied for a very short duration, and in this short duration it will excite all the molecules which that radio frequency energy is will correspond to the correspond to the resonance frequencies of the or resonance frequency of the nuclei which is present in the sample, and based on that we will get a spectra. Okay, so this radio frequency pulse is sufficient to cover a sufficient range of resonance frequencies in the spectra. So this is the duration for which the radio frequency has applied, tau, and this will cover a range of frequencies in the spectra, and only a small bit around the central frequency should be retained and the others filtered out by suitable electronic devices. So what we do is that we apply a range of frequency, but only a short range of frequency is selected, while the part which is belonging to this region, these are filtered out. These are filtered out by suitable electronic devices. So these devices filter out the frequencies which are outside these regions, so that only the nuclei which are having frequencies in this region will absorb the frequency and will show transition. Okay. So what happens? So we had earlier also we had understood the concept of rotating frame. So what is omega naught? Omega naught is the frequency with which the nuclei is rotating around about the z-axis. That is omega naught. And now we apply a radio frequency pulse, and this radio frequency, this is also an electromagnetic wave. Since it is an electromagnetic wave, it will have a particular frequency. Okay, it will have a particular frequency. So that is H1. That is actually omega 1, and omega I. What is omega I? The omega I is the frequency it is the frequency of the nuclei at the precisional frequency of the nuclei at the rotating frame. Precision frequency of the nuclei in the rotating frame. Okay, so basically what is happening is we have an external magnetic field H naught, and in presence of this external magnetic field, the nuclei is precessing about the magnetic field. Okay, now we apply a radio frequency pulse. This radio frequency pulse has a magnetic field H1, and corresponding to that magnetic field, it has a frequency omega 1, and the resultant omega I is the frequency of the precisional frequency in the rotating frame. Frequency in the rotating frame. So see this figure V. In the figure V, we have an external magnetic field H naught, and we have applied a radio frequency pulse in the X direction. Okay, now what will happen? The nuclei will experience a resultant magnetic field. The resultant magnetic field will be it will be resultant of the H1 and the H naught vector. And now because of this, the magnetization which was directed along the z-axis, now this magnetization shifts from the z-axis to the effective magnet along the direction of the effective magnetic field. Okay, so the precessional frequency in the rotating frame. So WIR is the precessional frequency in the rotating frame, and that is equal to omega I minus omega naught. Okay, since both are rotating in the same direction, so that is why it is omega I minus omega naught. And the corresponding amplitude of the magnetic field will be omega I minus omega naught by gamma. Okay, because as we know that omega I not equal to gamma H naught you can write. So H is equal to omega I minus omega naught by gamma. And what is the effective magnetic field? The effective magnetic field will be the resultant of H1 and the resultant of H1 and the HIR. So that is H1 square plus omega I minus omega naught by gamma whole square. So if H1 is very large, H1 is very large compared to HIR, then HIR will be almost along the H1 axis. So if this one is very, so what will happen that depending on which one is greater, whether this H1 is greater or whether this HIR is greater, this magnetic field will shift towards that vector which has a higher magnitude, right? So if the radio frequency has a very high magnitude, then the bulk magnetization will be directed along the x-axis or along the H1 axis. Okay, so this will gradually shift along the H1 axis. The magnitude will also be practically equal to H1, because if we consider that this is very small, this one omega I minus omega naught, this is very small. If we consider this as 0, then this H effective will align along the direction of the H1. And now what will happen? The nuclei will start spinning around it will start, it will precess about the H1 magnetic field. Okay. So what will happen that, so if you see this figure, consider this figure. So first the magnetization was directed along the Z axis. Now a radio frequency pulse is applied along the y direction, suppose. And now because of this magnetization starts rotating about this H1 magnetic field. And as the H1 magnetic field increases, this magnetization will gradually shift from this position, and it will gradually move along the direction in which the radio frequency is applied. Okay, so this radio frequency was applied in the positive y direction, and this causes the magnetic field to shift from the z-axis to the y-axis. Okay, and this is called the flip angle, theta. Theta is the angle by which the magnetization shifts from the XY plane. You can say it was rotating in the XY plane, and now it shifts from the XY plane towards the Y axis. Okay, so in the rotating frame, the direction of HRI effective acts as the axis of quantization of the spins, and they tend to orient with respect to this field. Okay, what will happen? The nuclear will start to orient with respect to the radio frequency field. And the frequency of the precession will be given by omega r equal to minus gamma h1. Omega r will be equal to minus gamma h1. If, however, the RF is applied for a very short time tau as a pulse, the magnetization will simply make a rotation in the YZ plane. It will simply make a rotation in the YZ plane. So if it is applied for a very short time, the magnetization will not align along the Y direction. It will now rotate along the YZ direction. So first it was rotating along the XY plane. Now because of the RF pulse, it will start rotating along the YZ plane. And the angle of rotation, remember this formula, the angle of rotation is given by theta equal to minus gamma h1 tau. Okay, so if tau is adjusted to cause a 90-degree rotation, then we say we have a 90-degree pulse. We have a 90-degree pulse. So, so basically, what we do is we control the duration for which the RF, what will be the energy of the RF pulse, and what will be the duration. And based on this, the magnetization will align, will shift from the z-axis to. So if we want this to align 90-degree to it or 180-degree to it, accordingly we will adjust the tau value and the gamma h1 value. Okay.
Okay, I have a question.
Yeah.
The z-axis is for the magnetic field, okay?
Yeah,
And xy is for the radio frequency, yeah?
yeah. The
Then,
radio frequency is applied in this y direction. Okay, y
okay.
direction, y
Then
direction.
how can I decide that I applied the radio frequency in y-axis or x-axis? Because of I see here in experiment if we rotate this, then the flip angle will change.
Yeah, the flip
Then
angle will
RF
change.
pulse is also change.
Yeah, the RF pulse, depending on the RF pulse, what is the energy of the RF pulse, the angle will change. The
Okay,
theta will depend on the energy of the RF pulse and the duration for which it is applied. So
okay. Then
depending on these two values, it can be that the theta can become completely like this. Then it will be 90 degree. Okay. So if the value is set to, if you set the tau and gamma h1 value to such a value that that whenever you apply this radio frequency, this magnetization will completely move from this z-axis to the y-axis. Then this is called a 90-degree pulse. Now you can set it to another value where this will shift the magnetization through 180 degree. It can align along from, it will move
minus
from the y to
z-axis.
the negative z-axis. Now, if you set the values in such a way that this pulse causes a 180-degree shift. So this will move from here to the, again, it will move to the negative y-axis. Okay. Now, if you set the values, so depending on, so it can be 90-degree pulse. So what does this mean? 90-degree pulse, that means that you have set the tau value and the gamma h1 value such that this frequency causes this magnetization to shift 90 degree away from its z-axis. Okay, it can be 90-degree pulse, it can be 180-degree pulse, it can be 270-degree pulse.
No, my question is okay, I set the angle pulse,
Yeah,
okay?
we set
So
the time duration and the pulse. Yeah,
RF pulse, okay na? So
yes.
my question is how can decide my radio frequency will given either in x-axis or y-axis suitable to my experiment?
Yes, it will
Yes.
be depending
How
on
it
your
can?
experiment.
Yeah.
So, so how how do you decide that?
I give this pulse is like that if I do any experiment in NMR and I applied RF pulse, okay, for short
Hmm.
duration of time,
Hmm.
then how can decide if this pulse is given to my perform experiment, then either the radio frequency goes to the x direction or y direction?
Yeah, it will go in the x direction or y direction.
This one is my
So
question. Then
there are
how it can
various
decide?
type of, so where there are various type of experiments, different types of NMR techniques, which we will learn in later lectures. So those so we will learn about the pulse sequence, pulse program. So depending on the molecule and depending on what we are trying to measure, that will control how we have to set this, what will be the duration and what will be this the energy of the RF pulse. So it will depend on, so you cannot say um, give a particular answer. So as we will move forward, we will understand that how do we decide this tau value and the gamma h1 value. Okay, so it
Okay.
is
Thank you.
experiment specific. Hmm. So now what happens now when this RF pulse is removed? When this RF pulse is removed, now the magnetization which was shifted from the Z direction to the X direction, now uh, this will again relax. This will relax, and in absence of the radio frequency pulse, it will again move back to its equilibrium position, and it will align in the Z direction. So when this relaxes, it follows a spiral path. It follows a spiral path, and this magnetization moves from this X direction and gets aligned in the Z direction, that is in its equilibrium position. Okay, so that is what it is said here. After the RF pulse is over, the effective field returns to H naught. The H naught is the external magnetic field. The external magnetic field was aligned along the Z direction. When the RF pulse is removed, the effective magnetic field will gradually shift from this X direction, and it will move and it will return to the z-axis. Okay. Now, yeah, so based on this, there is one question: at which condition will the spin be precessing along the H1 field? So just now we learned the formula for effective magnetic field. So effective magnetic field is nothing but it is the resultant of the H1 field and the H naught field. Okay, H1 field and the H naught field. Now, when will the spin be precessing along the H1 field? So it will depend upon the magnitude of H1 and the H naught. So if H1 is very high, then the effect, then the spin will then the nuclei will start precessing about H1. Okay. So it is a resultant, right? It is a resultant. So it will depend on which one is greater. So if the nuclei has to precess about H1, then what has to be large? H1 has to be large. Okay. So we will see the explanation. So H effective is root over gamma H1 square. So in terms of frequency, if you write this, so it is gamma H1 square, right? Gamma H1 square plus omega I minus omega naught whole square by gamma, right? So, so if this is so if this is very large, H1 is very large, then we can consider this as zero. This as zero. If H1 is very large, then omega I minus omega naught whole square can be ignored. Therefore, then what will be the case? Then H effective will be equal to gamma H1 whole square by gamma, and in this case, H effective will be equal to H1. So if we want the nuclear to precess about H1, about the amplitude of the radio frequency first, then the H1 has to be larger than the much larger than the effective magnetic than this H now. Okay. So you can see this figure also. Yeah. So you can look at this figure, and if you go through this figure, you will understand what is happening. Okay. Yeah. So moving to the next question, for a RF strength of 50 kilohertz in frequency units, flip angle for a pulse duration of 10 microsecond will be. So just now we learned the formula for flip angle. It is gamma H1 into tau, right? Gamma H1 is the, what is gamma H1? Gamma H1 is the frequency of RF pulse, isn't it? It is the frequency of RF pulse. And tau is the what? Tau is what? Tau is the time duration for which the RF pulse is applied. Time duration for which RF pulse is applied. So the flip angle means how much the bulk magnetization will orient away from the z-axis. What is the angle with which the bulk magnetization gets displaced from the z-axis? That is called the flip angle. So this flip angle will depend on two factors. One is the frequency of the RF pulse, and another is the duration for which the RF pulse is applied. So if you apply this formula over here, so what you will find, theta is equal to, so here it is given in frequency unit. Frequency unit means gamma H1, because we know that omega is equal to gamma H1, right? Omega equal to gamma H1. So directly you put 50 kilohertz, 50 into 10 to the power 3, and 10 microsecond. 10 microsecond means 10 into 10 to the power minus 6. And then if you calculate this, what value will you get? You will get 0.50. So this value is in radian. Okay. This value is in radian. Now from radian, how will you get this pi value? So if you consider a circle, then 0.5 radian means how much? 0.5 means pi by 2, right? So you can consider that 0.5 is pi. 0.5 is pi. If it was 0.25, it would be pi by 2. So in this way. Yeah. So this is shown how we have to solve this question. So this is the flip angle. The flip angle is given by gamma h1 tau. The value of gamma h1 is given in the question. It is 50 kilohertz, 15 to 10 to the power 3 into the magnetic field is 10 and the 10 microsecond. So you get theta 0.5 radian. And now if you consider a circle, 1.5 radian would be pi. Now if the value was 0.25, it would be pi by it would be pi by 2. Okay, 0.25, it would be pi by 2. Because if you start from here, then pi would mean that. So this is 0 degree and this would be 180 degree. So 180 degree would mean pi. And if it was pi by 2, if it was 0.5 radian, then it would mean that from this point to this point, so this would correspond to 0.25 or pi by 2. Okay. In this way, you have to solve this question. Now, what is the concept of strong coupling and weak coupling? Weak coupling nuclear system. So, the how do we understand this is we label the nuclei in alphabetical order. So, if AB system means that these A and B are strongly coupled. So the as we know the order of alphabets. So since B comes after A, so AB system means that this A nuclei and B nuclei are strongly coupled. AX system would mean that the A nuclei and the X nuclei are very weakly coupled. Are weakly coupled means that the chemical shift for A and chemical shift for X would be separated. There will be a large separation between the chemical shift of A and X. And if it is a strongly coupled system, an example of strongly coupled system is the AB nuclear system. It means that the chemical shift of A and B are very close to each other. Okay, are very close to each other. And what factor controls whether the two nuclei will be strongly coupled or weakly coupled? We discussed in the previous slides that the value of coupling constant J12, this value controls whether the two nuclei will be strongly coupled or weakly coupled. Okay, and one more factor is that it is basically depends on the resonance frequencies. So depending on what are the resonance frequency of different nuclei, it will determine what will be their chemical shifts, and it will control whether they are strongly coupled or weakly coupled. So what is an AX system? AX system means that the spins A and X have widely separated resonance frequencies compared to their J coupling constant. Compared to the J coupling constant, they are widely separated. So the delta separation between A and X is much higher compared to their coupling constant. ABX system means that the spin X is widely separated from both A and B. Spins A and B have similar resonance frequencies relative to JAB. Okay, ABC are strongly coupled system, while AX, AMX, AMQX, these are weakly coupled system. The relative magnitudes of the coupling constant and the chemical shift separation determine whether the spin system is weakly coupled or strongly coupled. So how do we determine whether the system is weakly coupled or strongly coupled? That will depend on the ratio of the coupling constant between the two nuclei and the separation of chemical shift between the two nuclei. So if the ratio is very large, it means that the two nuclei are strongly coupled. If the ratio is J by delta, if this ratio is small, then the nuclei are weakly coupled. So heteronuclear nuclear spin systems. This I have said in that this heteronuclear spin system means H1C13, H1N15. These ones, what do they have? They have stronger coupling constant. These J value are stronger. Okay, since they are stronger, their chemical shifts are very widely separated, or their resonance frequencies are very they have very large separations between their chemical shift. So one thing you have to remember that for strongly coupled systems, these quantum mechanical calculations are required. Okay, so here is an example. This was there in the slide also. So if we look at if this is an AB system. So for an AB system, we see the J by delta values. For different J by delta values, what is the spectra that we obtain for an AB system? So as we see in this figure, that as this ratio increases, the separation between the resonance frequencies of the A and B nuclei decreases. So here there is only one peak. They are very strongly coupled. And now as this value decreases, the it suggests that they are weakly coupled. Okay, the separation between them increases. Now, so now what does it suggest? That when J by delta is infinite, the spins are equivalent. The outer two transitions have zero intensities. Okay, these two transitions. So there are so these can have four different transitions, right? Alpha, 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 beta, beta, alpha, and beta, beta. So these are the outer transitions have zero intensity, and the inner two transitions have same energy. That is nu equal to nu1 equal to nu2 equal to half nu1 plus nu2. So these values, the frequencies, what are these relative intensity? So these are for the strongly coupled system. For strongly coupled system, the values for the intensity and frequencies, these values we have obtained through quantum mechanical calculations. These calculations are shown in the lectures. You can go through the lecture. But what you have to remember, the main thing is that this sine to theta, this formula you need to remember for solving questions. That sine to theta equal to 1 by root over 1 plus delta by j square. And what is this sine to theta value? This sine to theta value, it appears in strong coupling. It is a parameter which decides whether it is a strongly coupled or weakly coupled. And this factor, it changes the intensities and frequencies of transitions. Therefore, it is called strong coupling parameter. Okay. So we will solve one question to understand this better. So if the coupling parameter is theta equal to 22.5 degree, what coupling does the spin system experience? Okay, so if theta equal to 22.5 degree, then sine 2 theta would be how much? So sine 2 theta would be 45 degree, right? So sine 45 degrees 1 by root 2. 1 by root 2. And just now we saw the formula. So just in the solution. So I will solve this question first. So sine 2 theta is what? It is 1 by root over 1 plus delta by j whole square. Okay. So now in this question, you have been asked to find whether the spin system experience strong coupling or weak coupling. So how will you determine whether it is experiencing strong coupling, weak coupling, or relatively strong coupling? So that will depend on their J by delta value. Okay, that will depend on the J by delta value. So if the J by delta value is very high, then it would indicate that they are strongly coupled. If it is low, it would mean that they are weakly coupled. So you have to calculate the J by delta value. So here sine 2 theta is sine 45 degree. And from here you can calculate the value of J by delta. So sine 45 is 1 by root 2. And this will be equal to 1 by root over 1 plus delta by j whole square. Now what equation you will get? You will get here equation 1 by root 2 equal to you can consider, you can also think of in this manner 1 by root 2. 1 by root 2 you can write it in 1 by 1 square plus 1 square, right? You can write root 2, you can write 2 as 1 square plus 1 square. So root over 1 plus delta by j whole square. This would mean that delta by j is equal to, so if you compare the left hand side and the right hand side of the equation, then what you can say that delta by j will be equal to 1, right? So delta by j, if delta by j is equal to 1, then it would mean that this spin system is relatively strong coupling. Okay, why relatively strong coupling? Because as you see in this j by delta equal to 1, there is that these transitions, you can see small peaks because of these outer transition. Okay, but you cannot say it is strongly coupled, because if it is strongly coupled, then you would not see these. You cannot differentiate these different peaks. There would be only a single peak. So in this case, what you say that this, since j by delta, delta by j is 1, or you can say that j by delta is 1. So it means that they are showing relatively strong coupling. Okay. So yeah, similar to say, that was using the same concept, you have to solve this question. A molecule with two protons coupled to each other produces a spectrum of four lines. Produces a spectrum of four lines. Okay, so like this, you are getting four lines. Sorry, getting four lines. Okay. So two protons are coupled to each other, and the chemical shift of two protons are 2.7 and 3.3 ppm. Okay. So it means that it's like this. Okay. So one is coming at 2.7 ppm and another is coming at 3 ppm. 2.7 ppm and 3 ppm, it would mean that they're very closely, they're in, they're very close to each other, right? This is, you know that the center of this these peaks gives us the chemical shift. So if this is a doublet, then this center would be the chemical shift, 3 ppm. Okay. Now, what you have been asked to find, you have to find the coupling constant is given. The coupling constant is 10 hertz. The coupling constant is 10 hertz. And what you have to find? You have to find the intensities of the four lines in the decreasing order of frequency on a 100 megahertz spectrometer will be. Okay. So 2.73 means they are very closely spaced, right? So almost you will see that there are, there will be almost, they are very close to each other. Okay. So the J is given 10 hertz, and the chemical shift of the two protons are also given. So what is the separation? If you have to calculate the separation of the chemical shift, it would be how much? This is 3.0 minus 2.7. The separation of the chemical shift is only 0.3 ppm. Okay, 0.3 ppm. And now on a 100 megahertz spectrometer, this 0.3 ppm chemical difference in chemical shift would correspond to 0.3 into, you multiply this difference in chemical shift with the frequency of the spectrometer, 100 hertz. So you consider that 1 ppm, I had discussed in the last lecture, that 1 ppm is taken as 100 hertz. For a 100 megahertz spectrometer, 1 ppm would be considered as 200 hertz for a 200 megahertz spectrometer. Okay, so in this way, you convert ppm to hertz. Okay, so 0.3 ppm means 0.3 into 100, this is 30 hertz. So now you have got the value of J and you have got the value of delta. Now we have to calculate the intensities of four lines. So what will be the intensities of four line? So as we had seen, the intensities of the four line will be 1 minus sine to theta, 1 plus sine to theta, 1 plus sine to theta, and 1 minus sine to theta. So there are very detailed calculations for the as to how we derive these values. I would suggest you to go through the lectures. But since this is just for helping you in solving the questions, you can remember this formula, and this will help you to solve the question. So so now you have to calculate the value of sine 2 theta first. So if you calculate the value of sine 2 theta is 1 by root over 1 plus delta by j whole square, right? That was the formula. Sorry, this is not. This is delta by j whole square. So if you calculate this, you can calculate this value. So it will be 1 by, you put the value of delta and j. Delta will be 30, right? And j will be how much? It will be 10 whole square, and then you will get 1 by root 10. 1 by root 10. So if sine 2 theta equal to 1 by root 10, you can use the calculator and you can get the value of theta. You can get the value of theta. So this, so you do not need to find the value of theta. right? You do not need to find the value of theta. You just need to get the value of sine to theta. So once you get the value of sine to theta, then the intensities will be what? So if you calculate, you will get the value of sine to theta to be 0.32. Then the intensities will be 1 plus 0.32, 1 minus 0.32, 1 plus 0.32, 1 plus 0.32, and 1 minus 0.32. So the correct answer will be this one. 0.68, 1.32, 1.32, and 0.68. Okay. Just remember this formula and the intensities. What will be the relative intensities? It is 1 minus sine to theta, 1 plus sine to theta, and so on. Okay. Yeah. Now, another concept that was discussed in the lecture is signal to noise ratio. How do you improve the signal to noise ratio? So in an Fourier transform NMR spectrometer, what we do that we perform several scans. If we scan the if we apply a particular radio frequency, and we apply short burst of radio frequency for several times, then we can improve the signal to noise ratio. Okay, so remember that what is signal to noise ratio? It is the peak height above a mean noise level. So this concept was discussed in the lecture. Above, so there will be a lot of noise in that, and above a mean noise level, what is the peak height? What is the peak height above a mean noise level divided by the maximum peak minus peak separation in noise into 2.5. So the signal to noise ratio can be improved if we first, if we increase the peak separation. So if we increase the peak separation, if we increase this peak separation, then this value, this one will come, this one will decrease, this one will decrease, and overall we will get a high signal to noise ratio value. Okay, and another way of increasing the signal to noise ratio, if we increase the number of scans, or if we that is, it is because signal to noise ratio is proportional to root over number of sweeps squared. Therefore, if we increase the peak separation and if we increase the number of sweeps, the number of sweeps means number of scans that we are doing in 1 second, that if we increase, then we can improve the signal to noise ratio. Okay. So these two options are the correct one. Another concept was also discussed, slow passage versus pulsed excitation. So what does slow passage? So slow passage excitation means, so in a slow passage experiment, the magnetic field or radio frequency is swept slowly through the radio frequency of the nuclei in the sample. Okay, so like just now what we understood, that short bursts of RF pulse is applied, right? But before the development of this technique, earlier this slow passage was used. So in slow passage, what happened that there were so what we learned, that very short burst means they were applied for 10 to the power in microseconds, the pulses are applied. But in slow passage, as the name suggests, it means that they are given for a very long time. This radio frequency energy is given for a very long time, and because of this, so this is given for a long time so that this frequency can match the radio frequencies of whatever nuclei is present in the sample. Okay, the signal is detected as a resonance condition is met for each frequency. So since there will there is a sample, there will be different nuclei, and each nuclei will have different frequencies. And depending on the frequencies, they will absorb the energy, and it will show a peak depending on its resonance frequency. And this spectrum is recorded point by point. So it takes a significant amount of time. So slow passage, as the name suggests, it means you are applying it for a very long time, because the process involves scanning through the entire frequency range, detecting signals one frequency at a time. The signal to noise ratio is lowered. Why is it lower? Because since you are applying it for a very long time, you will also get peaks, very high peaks for the other than your interest, the nuclei of interest. There will be there will be certain other nuclei or noise that will also start showing peaks in that, and hence in slow passage the signal to noise ratio becomes lower. But in pulse excitation, what we do, we apply short RF frequencies. We apply RF frequencies for a very short duration of time. Okay, intense pulse of RF radiation is applied, and after the pulse, the nuclei return to their equilibrium states. And when it starts returning to their equilibrium state, it starts generating. We start recording. Because of the fluctuating magnetic fields, we can record say signals, or we can get a change in, yeah, electro EMF. We can record the EMF. Okay, that is called FID, free induction decay, that are detected as a function of time. This the time domain signal. Now, what is happening is we are applying the radio frequency in time domain, and this time domain is converted into frequency domain by Fourier transformation. Okay, the time domain is converted into frequency domain. So we are applying the radio frequency in time domain, but for obtaining the spectra, we need to convert this time domain into frequency domain, and this is done by Fourier transform, and this is mainly done by software that is present in the machine. So there is one question. I think not many. Yeah, two questions. So we will discuss these two questions, and then we will stop today's session. So in the slow passage experiment, a signal sweeps through the spectrum of 5,000 hertz, takes 23 minutes 20 seconds. In a Fourier transformation experiment of some 23 minutes 20 seconds. Okay. So we have used the slow passage experiment. Okay. And using the slow passage experiment, you have applied the signal for 23 minutes 20 seconds. 23 minutes 20 seconds. Now in a Fourier transformation experiment of the same sample. So you have a same sample, you are recording it using a slow passage experiment, and you are recording using a Fourier transformation experiment. And you in the Fourier transformation experiment, you record it has been said that, yeah, that one scan takes 1.5 seconds, and the time for Fourier transformation. So the time that takes for Fourier transformation means converting the time domain into frequency domain is 50 seconds. So now you have to find the signal to noise gain in the Fourier transformation NMR experiment. So what I was just discussing is that the slow passage experiment have a very low signal to noise ratio. Now, if you record the same sample in a Fourier transform NMR experiment, the signal to noise ratio increases. So in this question, what you have to find that compared to this slow passage experiment, this Fourier transform NMR experiment, when you perform the same experiment using this FT-NMR method, what is the gain in signal to noise ratio? Okay, that you have to find. So this is a very simple question. So first you calculate that for what duration this slow passage experiment was done. So it is 23 minutes, means 23 into 60 plus 20 means 1400 seconds. For 1400 seconds, you have applied the radio frequency energy, and you have recorded the spectra. Now in Fourier transform experiment, you are taking a single scan for 1.5 seconds. Okay, 1.5 seconds, and suppose now you have performed X scans. You have performed X scans. Okay, so this is in FT NMR, and this is in single passage. Okay. In single person. So for example, here it has been said that you have scanned the sample for 1.5 second, one scan in 1.5 second. And in this way, for example, let us consider that we have taken X scans. So then it would be 1.5 into X, and another 50 second is required for converting the time domain into frequency domain for Fourier transform. Now, if you have to calculate the, so if you can now, if you want to calculate the value of X, so this one will be equivalent to this one. So here you can get the value of X. So this value of X will come out to be how much? 900, right? So So as we saw, as we calculated that the signal to noise ratio is directly proportional to the number of sweeps scanned. So even if you divide this by 1.5, approximately what will you get? You will approximately, you can consider this 900. Okay. And here you have a gain of 30. Okay. So the correct answer for this question is 30. So did you understand this question? So just now I discussed, right? This signal to noise ratio is directly proportional to number of sweeps co-added. Okay, so that is why we calculated first we calculated that what are the number of scans that is performed for this FTNMR experiment, and we calculated that it is roughly equal to 900. And so this signal to noise ratio will be directly proportional to root over 900, that means 30. Okay, that means the noise signal to noise gain would be 30. Okay, now this is the last question of today's session. Last question of today's session. So how do you decide that in which direction the bulk magnetization will align? When the RF pulse is applied, what will be the along which axis this bulk magnetization will shift? How do you decide? So, consider this one. This is x-axis, this is y-axis, and this is z-axis. Okay. So what is said in this question is that a 90-degree x pulse. A 90-degree x pulse. What does 90-degree x pulse means? It means that the radio frequency is applied along the positive x direction. Radio frequency pulse is applied along the positive x direction. A 90-degree x pulse rotates the Z magnetization. Okay, so now the bulk magnetization is aligned along the Z axis, aligned along the Z axis in presence of the magnetic field, and it is aligned along the Z axis. Now an RF pulse is applied along the positive X direction, and this rotates the bulk magnetization from the Z axis to the minus Y axis. Minus Y axis means this one, right? This would be minus Y axis. Minus Y axis. This rotates the Z magnetization to the minus Y axis. Now what you have to find is that if this 90-degree Y pulse, so if you applied the pulse along the Y direction, so when you are applying the pulse along the X direction, the magnetization shifts from the Z axis to the minus Y axis. But if you apply the pulse along the Y axis, what would be the shift? So there is another case. This is the second case. Now what you have done, that you have applied the RF pulse along the y-axis, along the negative y-axis. Sorry, I've drawn it wrong. Along the negative y-axis means you have applied it along this direction, right? Along this direction, you have applied the RF pulse. And so in this case, in which direction will the bulk magnetization shift? Consider this is the B naught bulk magnetization. So where will the magnetization shift in if this RF pulse is applied along the negative y-axis? So how do you calculate this? So for this, you have to apply the right hand thumb rule. Okay, so the thumb would point towards the direction in which the RF pulse is applied. So in this case, so in the first case, consider the first case. In the first case, the RF pulse was applied along the positive X direction. Okay, so you align the thumb along the positive X direction, and your fingers will the direction in which your fingers curl would indicate the direction in which the pulse will rotate on application of the RF pulse. So the bulk magnetization was in the Z direction, and we have applied the RF pulse in the positive X direction. So what will happen? It will move to the negative Y axis. Okay, you can do this and you can understand. You can do it on yourself, and you can considering a 3D geometry, you can understand what is happening. So, but if you apply the pulse in Y direction, negative Y direction, now we have applied in the negative Y direction. So this would cause the bulk magnetization to shift from the Z direction to the, now what direction will it shift to? Negative X axis, right? So our X axis is in this direction, and you have applied the RF pulse in negative y-axis. Now, so our finger will curl towards the negative y-axis. So the bulk magnetization will shift from the z-axis to the negative x-axis, right? We shift in this direction. We shift in this direction. Okay. So, this direction. So how do we decide the direction in which the bulk magnetization will shift? So that is indicated by using the right hand thumb rule. Right hand thumb rule, you have to apply the right hand thumb rule and you have to, then you can find out in which direction the bulk magnetization will shift. Now, for example, if you applied this other than 90 degree, if you apply a 180-degree pulse, then what would be the axis? This question can also be asked. So you are not applying a 90-degree Y pulse, you are applying a 180-degree pulse. So in this case, what would happen? So first it was index Z direction, then it will move to the negative X direction, then it will move to the minus Z direction. So okay. So in this way, it will move from Z to ZX plane. Okay, it will move in along the ZX plane. Start rotating about the ZX plane. Now, similar way, if this magnetic field was applied in the, for example, here it is X pulse, but if it was applied in the minus X direction, RF pulse is applied in the minus X direction, then again you can calculate that. You can find out the magnetization will shift from the Z to the X direction. So in this way, you can do this and you can try this on your own and you can understand how this is happening. You can understand this. Okay, so the correct option is option C. Okay, positive x-axis. So you have applied the 90-degree, you have applied the pulse, 90-degree pulse along the positive y-axis, and this causes the bulk magnetization to shift to the positive x-axis, right? Positive x-axis. I hope that is clear. So these were all. This was all from my side. If you have any more questions and doubts, you can ask me. I hope this question is clear. So I will draw it in a better manner. This is the z-axis. This is the y-axis. This is the x-axis. In the question, what you have been told? You have been told that the 90-degree pulse is applied along the positive y-axis. So it has been applied in this direction. This is the 90-degree Y pulse. So accordingly, under bulk magnetization, in equilibrium will be along the z-axis. When this is applied, this will move. So it is in this direction. It will move in this positive X direction. Okay. Positive X direction. So, okay. So that was all. Yeah. I hope this session was useful to you, and now you can attempt week 3 questions and try out. So you will find that if you now that I have discussed these questions, you will find it simple to solve these questions. And in case
Thank
you
you so
face
much.
any, yeah, in case you face any difficulty, we can again discuss it in the next session. Okay. Yeah. Thank you.